Hi everyone. Now that we have had a look at how you get the Euler's formula where there's an equivalence between the exponential form and the, well, cosine and the sine form of a complex number, we can do a few more things with it. Well, firstly, let's look at how this exponential form actually inherits all the properties of the same properties as the cosine and sine form. Well, firstly, obviously it's cyclic. So if you think about it, complex numbers, um, if you have a complex number, it should be the same as a 360-degree rotation. So if you increase the angle or the argument by 360 degrees or 2 pi radians, everything should be the same. By the way, I'm using theta as the variable here because, well, we are actually referring to the angle or the argument of the complex number. Yeah, and then so it will be also the same if you increase, well, any random multiples of 360 or 2 pi. And that obviously this is very clearly true for a cosine and sine, and the exponential form simply inherits this. The other thing, obviously, this particular expression only has the length of 1, because if we want to check the distance of this or the modulus of this complex number, it's, well, cosine squared plus sine squared equals to 1. So the length is actually 1. And if we want to change the length, we need to multiply it by a distance. So basically, the modulus, and that's what's called modulus because it's just simply a multiplier. So r e to the power of theta I, and in here what you have is basically a complex number with the length of r and the angle of theta. This also conforms to our expectation with multiplication of complex numbers. So if we have two complex numbers, we have z1 equals to r1 e to the power of theta 1i, and we have a second one, z2 equals to r2 e to the power of theta 2i. And if we multiply them, obviously the length, the modulus, they get multiplied by each other. And as you can see, the exponential part, you essentially have the application of index law, because you have two exponentials of the same base multiplied together. So you simply have to add their exponents. And this conforms exactly to what we have done with the multiplication of complex numbers. When you multiply two complex numbers together, you multiply their modulus and add their arguments. Now, that is also as a further consequence with De Moivre's theorem, because if you remember, whatever, De Moivre's theorem, what you have is basically saying if you have a complex number in this form, we should end up with cosine and theta. So when you raise the complex number power, you just multiply its angle by whatever that power is. And if you simply do this way, it requires a bunch of operations with trig identities. But if you use the exponential form, say e to the power of theta I. And if you raise the whole thing to a certain power, all you end up with is, once again, a simple application of the index laws. And it's just so much more straightforward than operating with the trig identities. Next part is worth mentioning is the conjugates of complex numbers. So if we have, let's say, e to the power of, let's say, more general. So if we have a complex number, z equals to r times e to the power of theta I, we can plot it on number plane. Or rather the complex plane, because the vertical axis is complex. And then we'll say, okay, this number is r e theta I. Obviously, it has the angle of theta and the length of r. Now, based on what we've done with conjugates, we all know that it's a reflection about the real axis. So the horizontal component or the real component is the same, but the imaginary component will be the opposite. So the angle will obviously be minus, but the length will be the same. Yep, and that's our conjugate. So we can safely say that the conjugate of z is r e to the power of negative theta I. This actually leads to a fairly interesting relationship, because if we have a complex number, e to the power of theta I equals to cosine theta plus sine theta I, and its conjugate e to the power of minus theta I equals to cosine theta minus sine theta I. Okay. We do have a pair of conjugates. Let's call them 1 and 2. If we add them, what we end up with is, well, on the left-hand side, we have e theta I plus e to the power of minus theta I. On the right-hand side, as you can see, plus sine theta I minus sine theta I, they actually cancel each other out. So all you have is 2 cosine theta, and that means you can in fact represent cosine theta in terms of complex or exponential form of complex numbers. So there's actually a relationship between cosine theta and a pair of conjugates of complex numbers. And you can do exactly the same thing with sine. So all we do is simply now, instead of adding, we subtract the conjugates. So e to the power of theta I minus e to the power of negative theta I. And as you can see here, cosine minus cosine is 0, plus sine minus negative sine. So we actually end up with 2 sine theta I. And once again, if you divide both sides by 2i, we can see that sine theta can be expressed as e to the power of theta I minus e to the power of negative theta I over 2i. Now let's have a look at how some of these relationships can be used to work on trigonometric identity problems. So, for example, let's look at the first one. It's asking us to show that cosine to the power of 4 theta is the same as 1 over 8 times cosine 4 theta plus 4 cosine theta times 2 theta plus 3. Of course, if you really want, there's probably ways to do this purely relying on trig identities. But now that we have these relationships, it's probably wise to actually use them. Okay, so firstly, if we look on the left-hand side, we can see that it's a power of 4. So we can write as cosine theta to the power of 4. And since it asks us to use the expansional form, we just replace cosine theta with e to the power of theta I plus e to the power of minus theta I over 2. So we can just do this. And to the power of 4. And of course, we can take the 2 out. So we end up with half to the power of 4 is 1. To the power of 4 is 1/16. So what we actually end up with is, as you can see, rather than some very complicated trig identity, we end up with a binomial expansion. That simplifies things greatly, because now we can just say, okay, 1/16 stays here, but inside, what we can have is, so it's to the power of 4, so it should be 1, 4, 6, 4, 1 for the coefficients. And we end up with e to the power of 4 theta, because it's to the 4. Plus, so coefficient will be 4, e power lose a power, and then the other one gains a power. Yeah, and then plus 6, still lose 1 more power. The second term gains 1 more power. And then plus 4, e theta I, so lose 1 more power. The other one gains 1 more power. And then plus e to the power of 4 theta I. As you can see here, what happened is we have managed to convert what potentially may be a very convoluted trig identity problem into a much more straightforward binomial expansion. Even though they end up quite a few symbols, but as you can see here, they all follow very simple rules. So what we end up with is e to the power of 4 theta I. Let's simplify everything. Plus 4 e to theta I plus 6. Well, yeah, positive, negative, they cancel each other out, so we only have 6 left. Plus e to the power, correction. Yeah, it's 4 e to the power of negative 2 theta I, then plus e to the power of 4 theta I. Okay, some of you may have noticed that these terms and these terms are all conjugates of each other. So what we can do is we can actually gather them together and say, well, we have e to the power of 4 theta I plus e to the power of minus 4 theta I plus 4 e 2 theta I plus 4 e minus 2 theta I plus 6. And then if we look at this, if we bring the divide by 2 here and divide by 2 here, what do we end up with? And then replace this with an 8. What we end up with is, as you can see, this part is simply Also last bit 2 as well, almost forgot. And then what we end up with here is cosine, yeah, because we have a complex number plus its conjugate divided by 2, so it's the cosine of the angle. Plus, okay, 4 times, as you can see here, 2 theta minus 2 theta, once again, conjugates, divided by 2, that's cosine again. And then, of course, last bit is 3. And it is, in fact, what we were meant to do. As you can see here, these the expressing trig ratios with exponents or complex numbers actually can simplify some of the trigonometric identity problems quite substantially. Now let's look at a slightly more complicated example where we have a few more things going on. So we're trying to show that cosine alpha minus cosine beta is the same as minus 2 times sine alpha plus beta over 2 times sine alpha minus beta over 2. Okay, so we're actually going to probably work with the right-hand side at this time, because if we simply swap cosine into with the exponential forms, I don't think that helps that much. But if we swap sine with the exponential forms, you can see that what we end up with is expansion of a binomial expansion. So let's do that. Now, to make things slightly easier for us, we just replace alpha plus beta over 2 with theta, and alpha minus beta over 2 with phi, so that we don't have to write all of this stuff every time, which should help us speed up things a bit. So what we can do is, now we replace these variables with theta and alpha respectively, so we end up with 2 sine theta sine phi, and then we can swap them out with their exponential form. So minus 2, if you remember, e theta I minus its conjugate over 2i, and then times sine phi, which is e to the power of phi I minus its conjugate over 2i. And we can actually take 2i times 2i out, because 2i times 2i is minus 4. So minus 2 times minus 1 on 4, that should give us a half. And then inside, that's just regular expansion. We're multiplying 2 terms with the same base. So we simply add their indices. So once again, index laws. Minus e minus theta plus phi minus theta, sorry, I here, e to the power theta, it's a minus here as well, theta minus phi I, and then plus e minus theta minus phi power of I. Cool. Okay, and now, more interestingly, we can see that the sum of alpha and theta and phi, and the difference actually correlates with our alpha and the betas, because theta plus phi in this case is alpha plus beta over 2 plus alpha minus beta over 2, which is alpha plus alpha is, well, 2 alpha plus beta minus beta, and they cancel out. 2 alpha over 2, that is just alpha. And then theta, sorry, minus phi, well, it's alpha plus beta over 2 minus alpha minus beta over 2. As you can see here, once again, alpha cancels out. Beta minus negative beta, that's 2 beta. 2 beta over 2 gives us beta. So in this part, now we can replace all of them with alphas and betas. So theta plus phi is alpha I minus theta plus phi, so that is minus theta minus phi, which is minus beta. So we end up with e to the power of minus beta I minus theta minus phi, that's just beta I, and then plus in the end. So this is minus theta plus phi, and which is e to the power of minus alpha I. As you can see, we once again end up with 2 pairs of conjugates. So we just move things around. We can say, well, half e alpha I minus, plus e minus alpha I minus, we can factor minus out. So e minus beta I plus e beta I. Oh, it's horrid, this beta. Okay, yeah, let's just do this as well. And as you can see here, when we divide everything by 2, we end up with, well, alpha e to the power of alpha I plus e to the power of negative alpha I over 2. That's just cosine alpha, yeah? And then e to the power of beta I plus e to the power of minus beta I over 2. That's just cosine beta. Yeah, and that is pretty much it.